Okay, so now we're going to talk about 29.5, 29.6, 29.7, particle wave duality, the wave nature of matter, and the Heisenberg uncertainty principle, as well as the concept of particle wave duality in general. Okay, so particle wave duality comes out of the fact that in a diffraction grating experiment, you see, or like double slit, you see that light is interfering with itself and passing through and creating this interference pattern. Okay, so that makes a lot of sense. But don't forget that the photon has momentum, just like a particle. So already we see this correspondence between the momentum of a photon and the wavelength of a photon, as well as de Broglie reasoned, this guy, French dude, he said, all right, if P equals h over lambda, well then how about lambda equals h over P, except instead of P being, any photon of a momentum of a photon, well, this could be true of any particle where momentum could be mv. And so then you could calculate what the wavelength of an electron is, for example, and that's called the de Broglie wavelength. And it's a function of the momentum of the particle. So, for example, a 3 kilogram bowling ball moving at 10 meters per second that you threw down the alleyway will have a wavelength of this. Very short, almost negligible, but right there shows you that this bowling ball has something of a wave nature to it. Okay, it's obviously smaller than anything in the known universe, but the point is that it's possible. And this diffraction pattern is made from electrons, so that shows you right there electrons have a wave nature. So you can use the momentum of a particle gives you a wavelength, just like the wavelength of a photon gives it momentum. So electron microscopes are one example of using the electron's wave-like nature to actually image things. It has shorter wavelengths than regular photons, which allows us to have very high-resolution images of a shark tooth, I guess. That's not very impressive because teeth are not super small. Who chose to use that picture, for heaven's sakes? Show me a picture of a molecule. Okay, so these are pretty cool, the way these microscopes work, but this is just showing you that there's an interference pattern as the electron scans across the surface, and the detector measures the intensity, and the intensity turns out to be, the shape of the object, basically. Okay, so that's just we're talking in general of the wave-like and particle-like nature of a electron or something. Okay, so the Heisenberg uncertainty principle says that the better you know the wavelength of something, the less you know its momentum, and vice versa. The very interesting thing that this plot is showing you here is that this diffraction pattern that shows up in a double slit experiment, it happens whether or not you shoot a billion electrons at the same time or one electron at the same time. And that means that the electron itself is interfering with itself. It's an extended phenomenon that passes through both slits and creates a dot on the wall when it gets there. And so electrons and photons and protons all produce a diffraction pattern, which gives credence to the idea that particles have both a momentum and a wavelength. And there's no better example of it than the double slit experiment. And in this case, our d sine theta equals m lambda, which we used for photons, is also true for the wavelength of the proton or the electron, which is kind of amazing. So then the Heisenberg uncertainty principle says that, okay, well, if you're going to measure something, the uncertainty in your position is on the order of the wavelength of light that you're going to, or the wavelength of the electron that you're going to use to image the thing. Okay, and then the uncertainty in the momentum is h over lambda. Okay, and h over lambda tells you that, it's the same thing. It's a function of your wavelength that you're probing with. But the limit on your knowledge of either the momentum or the position is highly dependent on the wavelength that you use, but also you cannot know something better than this combination of momentum and position. So in other words, if you try to measure the location of something very precisely, let's say this electron is right here. When you go to measure it, you shine a photon at it, bink, and you move it a little bit during that measurement. So when the light bounces back to see where it was, you've been jiggling it around from all those photons. So you're trying to measure the smallest possible thing, and you can't get better than a, if you're trying to measure its position exactly, you're going to end up kicking it around when you measure it, and then its velocity is going to change, which means you've altered its momentum in order to get a precision measurement of its position. Or by the same token, if you want to measure its velocity, which means as it moves along, you have to go tick, tick, and then measure delta x and delta t here to measure its velocity as it moved from here to here. But when you go to measure that, you're going to disturb the locations, those two x coordinates, so you're not going to get a great measure on either of these things. And it turns out that affecting the x affects the momentum, and measuring the momentum affects the x, because you're altering both things by your measurement. So you cannot know both of them better than this relationship. There's a fundamental intrinsic uncertainty in locating something or measuring the momentum of something in the universe, and that's the Heisenberg uncertainty principle. You cannot get better precision than that, and that's kind of amazing. So let's say you can measure the accuracy and location of an electron to 0.01 nanometers. What's the uncertainty in the velocity then? Okay, so we just use this equation, delta x, delta p has got to be greater than h over 4 pi. We plug in our, we solve for our uncertainty and momentum, h over 4 pi times our uncertainty on position, and there's our uncertainty on the momentum, and then that is equal to mv. So then you divide by the mass, and you get that the uncertainty for the velocity is 5 million meters per second. And then you can solve for the kinetic energy of the electron at that speed. So that's pretty crazy, right? Blah. Let's see. And so there's another Heisenberg uncertainty principle or relationship between energy and time, and there's a minimum uncertainty on knowing both of those things at the same time. How much energy is being used at a certain time. Both those things, since energy is a function of time, the less you know the time, the less you know the energy, and so on. Or vice versa. Okay, so yeah, so for both of these, you're going to have to be able to do these types of calculations in these examples where it says, oh, the uncertainty on your time is this. What's your uncertainty on your energy? Or the uncertainty on your momentum is this. What's the uncertainty on your position? So be able to do those types of problems. Okay, 29.8, the particle wave duality reviewed. And so you've got an electron with momentum, you've got a photon with momentum. Both these things have wavelengths now, we've realized. So that means everything has a particle and a wave aspect. So to see the world in a grain of sand, and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour. That's a nice little poem there. But that is the, yeah, that's pretty cool. Blah, blah, blah. We've got another example here. Yeah, find the momentum of this photon. It's very simple. You just P is h over lambda. And then what is the recoil velocity of a particle dust if it's hit by this 550 nanometer wavelength photon? So you can solve for V equals the change in momentum here divided by m, and get the change of velocity. So when a photon hits a grain of dust, it has essentially no recoil velocity, but it's very small. Okay, so if you got enough photons, you get a recoil of that. It could, add up enough photons together. If you had 10 to the 18 photons, then you might get 1 meter per second motion out of that dust particle. Okay, so that's the end of that. See you guys later.